Okay, so far we have learned that in order that slip may occur, which in microscopic condition we call it as dislocation of motion to occur, then the sigma y should be above certain value, should be met maximum. Sigma y here is the axial stress, such that the value of the sigma y will be equal to this formula, the critically resolved shear stress divided by the maximum cos phi and cos lambda. So in this case, then we will find that sigma y value should be equal to 2 times of the value of the critically resolved shear stress. And this is what can be seen from plastically stretched zinc single crystal, that deformation will occur along the slip plane of its crystal system. This direction of the force, slip plane will occurs. Large number of dislocations are generated on the slip planes as they leave the system. They form these shear bands. Example for deformation of single crystal. If we have here sigma, the axial stress is 6,500 psi pound per square inch. Okay, and we have this slip. We have the slip plane. To make an angle of lambda 35 degree. So the lambda is 35 degree between the force and the direction of the what do you call it? The slip direction. The slip direction is 35 degree. The phi is 60 degree, means the angle between the area, the cross-sectional area of the ends of the bar, of this structure to the normal of the slip plane. The angle is 60 degree. If the tau CRSS, the critical resolved shear stress, is known to be 3000 psi, and the sigma is 6500 psi, will the single crystal yield or not? So it means will it deform or not? If not, then what is the stress needed in order that to make this crystal to yield or to deform? Let's calculate now first the shear stress. This stress equals to the sigma times cosine lambda times cosine phi. Here the sigma is 6,500 psi pound per square inch. The cosine 35 degree, cosine 60 degree. So we obtain the tau to be 0.41 times 6,500 psi. Tau, the shear stress equals to resolved shear stress equals to 2,662 psi. And this value is still lower or smaller compared to the critical resolved shear stress, which is 3,000 psi. So it means the crystal does not deform, does not yield. So if we want to make the crystal to deform, what stress should be required? So the tau should be then, the tau CRSS is 3,000 psi. The sigma y, which is equal to the sigma y, equals to cosine lambda cosine phi, and the cosine lambda cosine phi value is 0.41. So from here we can calculate sigma y to be equal to 3,000 psi divided by 0.41, or 7,325 psi. Okay. So for deformation to occur, the applied stress must be greater than or equal to the yield stress, which is 7,325 psi. What about now when the system is polycrystal, when the material is polycrystal? What can occur? In the previous examples, what we have been discussing is when the material is single crystalline structure. So when it is in polycrystal, there will be boundaries between the crystals, between the grains. Stronger grain boundary will create pin deformation. Okay, so with polycrystal, usually the yield stress will be higher because the grain boundary will pin the deformation. The slip plane and direction change from one crystal to another. In polycrystal, which has each crystal will have different crystal orientation, right? It means the slip planes for each crystal will also be different. The direction will also be different. The lambda angle, the phi angle will also different, change from one crystal to another. And as a result, the tau r, the resolved shear stress under applied axial stress here, yeah, the resolved shear stress will be different for each of the for each of this crystal, yeah, because each of the crystal has different orientation. This one, for example, the slip crystal plane is in this direction. This one has this direction, certain angle. This one has this direction to this angle, etc., etc. Okay, so the tau r will vary from one crystal to another. Then, crystal with the largest resolved shear stress will yield the first, will deform the first. Then, only after it deformed, the other crystals with less favorable orientation will yield. So slip direction vary from crystal to crystal. Some grains are unfavorably oriented with respect to the applied stress. Even those grains for which cos phi, cos lambda is high may be limited in deformation by the adjacent grains, which cannot deform easily. Dislocation cannot easily cross grain boundaries because of changes in direction of slip plane in disorder at grain boundary. Okay, then dislocation will be locked. It cannot move. It moved to the edge of that crystal, but then it cannot further move to the other crystal easily because the direction of the crystals are different. So then that is why it is not that easy for the dislocation to get to the edge of the material. That is why polycrystalline metals are stronger than single crystal. Of course, the exception is with the perfect single crystal. If you have a perfect single crystal without any defects inside, then this is stronger than polycrystalline. But when it does have even a single defect or multiple defects, then that single crystal will be easily deformable compared to polycrystalline material. Anisotropy in the yield stress can be induced, yeah, by rolling polycrystalline metals. So for example, if we have anisotropy means that it has different value of yield strength depending on the direction of where you are pulling. If you have material, polycrystalline material, whose crystalline grains are more or less what do you call it, spherical, yeah, or granular, yeah, then usually you will have an isotropic property. It means that the value of the sigma, let's say for example for yield strength, will be the same, either vertically, horizontally, or diagonal. It will be the same since grains are approximately spherical and randomly oriented. However, when you do rolling means that you apply stress, you are what do you call it? You put a very heavy load and direction, and then you press that material so that the material becomes thinner. Yeah, it becomes thinner. So what happened then? The crystalline structures within that material will also change. It will also change, so it will go towards the rolling direction, yeah, towards like this. So then you have different. So you start to have more orientation of the crystals towards the rolling direction. It means then anisotropy will occur because the rolling affects the grain orientation and shape. the sigma y in this direction will be different than the sigma y in this direction. An example here is given when cylinder of tantalum is machined from a roll plate. Yeah, this is the rolling direction. Okay, then fire the cylinder at the target. Yeah, for example, like this. Then you will have a deformed cylinder. So this is at the as seen as from the end view of the cylinder. Yeah. The non-circular end view. So here you see that it is not circular but a little bit elliptical. This shows the anisotropic deformation of the rolled material. Okay. So we have seen how deformation occurs, yeah, from the motion of dislocation. And now, based on the rolling, also we can make the crystalline structure shape to be changing. Can we exploit this property to strengthen the material? Yeah? The ability of a metal to deform will depend on the ability of the dislocation to move, yeah, with relative ease under loading condition. If it is a single crystal, then the dislocation will move along the slip plane, yeah, which will depend on the crystalline structure. Restricting the dislocation motion will inevitably make the material stronger. So you will need more force to induce the same amount of deformation. If we prevent this motion of dislocation to occur, so we just confine the dislocation to be in that region, so that it cannot move, yeah, move by the breaking and the reforming of bonding, as we have discussed earlier. That way, then we can make the material stronger because we prevent it from deforming. Okay. So, what are the mechanisms that we can use to strengthen single phase material? The first one is by reducing the grain size. If it were polycrystalline, yeah, by making the grain size, the crystalline structure, the crystal to be smaller instead of bigger crystal, then we can strengthen the material. How come? Yeah, as you mentioned, when the grain size is large, of course, that it means it contains more number of single crystalline state. Then the motion dislocation can easily occur within that single crystal. So if the number, if the grain if the size of the grain is large, then this single crystal structure within that material can be easily deformed. If we make the grain size to be smaller, then it means we make a large number of grain boundaries. Yeah, even if deformation occurs within a single grain, this deformation can hardly be transformed to the other grains because each grain will have different crystal orientation. So as a result, the whole system will be stronger. Second method to strengthen material is by solid solution alloying. So by introducing impurities into the material. How come that it becomes stronger? As we mentioned, as we have learned in the previous session, that dislocation motion can occur when there is this Berger stress field, that can be that tries to move, whenever we apply load. Uh, the bonding between the plane is broken and then reform at different place, and eventually this slip plane or the edge dislocation will appear in the edge of the material. So when we introduce impurity into the vacancy, So it means then it will be more difficult for the plane to be able to broke the binding and then reform with the plane on the adjacent side on its vicinity. Yeah, because it is being prevented by the impurities introduced into that material. So by making an alloy, by introducing impurity, introduce different kind of material, maybe with smaller element, smaller size element into the gap between the planes of that crystal, then we can strengthen that metal. The third method is by strain hardening. This is by putting strain into that metal material to make the dislocation to untangle to each other. Yeah, we will make it clear in the next slide. Ordinarily, strengthening mechanism will reduce ductility. How come? Why? Yeah, because ductility, remember the definition of ductility from the previous chapter. Ductility represents the easiness, how easy it is for deformation to occur of for that material, for that metal. So it means when we strengthen the material, it is harder for us to deform that material. So making a material stronger means basically uh, making it to be less ductile. Ductile is again the ability of material to be easily deformed. So let's now discuss in more detail each of the strategies to strengthening the material. The first strategy is to reducing the grain size of that material. So grain boundaries are barrier to slip. Yeah, remember like this. When you have this grain A with its internal slip plane and internal edge dislocation. So when you apply force, the slip plane may occurs, yeah, and may slide and move, yeah, dislocation motion until it reaches this edge. Yeah. But since it is multiple boundary, multiple grain, when it meets this grain boundary, that slip will be stopped. It cannot move further because in the next grain, it has different crystal orientation. It is not that easy for this slip to be transferred to the another grain due to this to the existence of this grain boundary. So barrier strength increases with misorientation. The more, yeah, the more the angle or the orientation of these two grains are different, then the stronger the barrier. If it is only slightly misoriented, of course, the slip plane may be easily transferred to the next grain. Okay, high angle boundaries therefore are better in blocking the slip. If you have smaller grain size, if this grain is smaller and small, this also smaller, it means then you have more barriers, right? Because um, each grain is smaller, and there are more barriers between the grains rather than if you have large grains. Yeah, as for example, let's say I give an example in geographical term. Yeah, if you have only in Northern America, you have only three countries: Canada, United States, and Mexico. You have only that uh, borders, yeah, the upper border, the horizontal line, yeah, between Canada and United States and between United States and Mexico. But let's consider, for example, Europe. Europe has smaller countries, yeah, more countries, smaller but more countries, more number of countries. You have Netherlands, Germany, Belgium, Liechtenstein, Czech Republic, Slovakia, Slovenia, what else? Romania, Bulgaria, and Hungary, etc., etc. You have more countries and you have more borders between them, right? So that creates more strength, a barrier. So that similarly, like that with crystal, if you have smaller grain and you have more grain boundaries, which will block the slip dislocation to move to the edge. Okay. Grain size can be changed by processing. By certain processing, we can change the grain from large to be smaller. So here, this is the Hall patch equation. The yield strength will be equal to the sigma 0 plus the K, a constant Ky, the yield constant, times D power minus half. So if D is made to be smaller, okay, so D minus, so this is sigma y equals sigma 0 plus Ky divided by square root of D, right? If D is smaller, so this term, this Ky term, if D is made smaller, this term will be made larger. It means the yield will increase. Okay. By reducing the grain size, you increase the yield strength. This is an example of grain size strengthening. You have a brass alloy which has 70% weight copper and 30% weight of zinc. According to Hall patch equation, this equation, you have the data here. This is the graph. When the grain size is increased, this is minus, so it means the grain size is actually decreased. Then you will have larger yield strength. You see here, the grain size is made smaller. Then from 10 to the power of minus 1 into 5 times 10 to the power of minus 3, or 5 micrometer, the yield strength will increase linearly according to this constant gradient Ky. Okay. Second strategy for strengthening is by using solid solution. So in solid solution, we introduce impurity to the metal. Impurity atoms will distort the lattice and then generate stress. The stress will produce barrier for the dislocation motion. So you prevent the defect to travel along that crystalline structure. For example, here, usually that impurity is smaller. That to become the substitutional impurity, you introduce this impurity. This impurity will generate local stress at A and B that opposes dislocation motion. So this dislocation motion here will go to the right, but this stress A will oppose that. Similarly, at this B to the left, but this B will oppose that. So eventually, it cannot move. The dislocation doesn't move. You can also introduce larger substitutional impurity. The impurity will generate local stress C and D that also oppose the dislocation motion to the right. So either way, either by smaller or by larger substitutional impurity, you can prevent dislocation to move. So alloyed metals that therefore are usually stronger than their pure base metal counterparts. For example, normal iron, just iron is usually weaker compared to steel, stainless steel. Stainless steel is iron which is being diffused with impurities such as carbon and chromium atoms. If iron in its original form, it is usually malleable. It can easily be deformed, very ductile, and can be easily oxidized. Therefore, let's say cars, plane, never they are made from pure iron. They are usually made with alloy of iron, made into stainless steel, for example. So interstitial, why is that? Interstitial or substitutional impurities in a solution will cause lattice strain, also known as distortion in the lattice. Then the strain field around the impurities will interact with the dislocation strain fields and impede the dislocation motion. Impurities tend to diffuse and segregate around the dislocation core to find atomic sites more suited to their radii. This reduces the overall strain energy and anchor the dislocation. The dislocation is anchored. It means it cannot move anymore. Motion of the dislocation core away from the impurities, move it to a region of lattice where the atomic strains are greater, where lattice strains due to dislocation is no longer compensated by the impurity atom. And so move this impurity away from the impurities, it will move to a region of lattice where the atomic strains are greater. So it is just being prevented to move the dislocation. So this is the illustration of the interaction of the stress field. Consider the stresses around an edge dislocation. Yeah, the extra half plane acts like a wedge. So above is compressive because it is being compressed. Below is where there is a vacancy here in the plane vacancy at area distortion, area dislocation or area defect. It will have a tensile stress. And when we introduce an impurity atom, this will create tensile, right? Because this impurity is still smaller than the host atom. Yeah, it will create tensile because or being stretched away from each other. But when we have larger substitutional atom, the surrounding atom will be compressed by this larger atom, yeah, because they will have smaller distance to each other. That is why they are in compressive state. So when this one is compressive, yeah, this is tensile. Here at the compressive state, you introduce impurity, smaller substitutional, which will create a tensile tensile stress field. This will compensate with the compressive state in this upper half. The stress will relax. Alternatively, you can introduce larger substitutional atom in the bottom part, in the lower part, which will create compressive stress, and this will compensate the tensile stress in the original condition. Yeah, something like that. However, when you also can introduce the substitutional smaller atom impurity into the lower part, but not at that part, at that dislocation, a bit away. And you have tensile also. This one will have tensile. There, it will repel each other. Yeah, so it will move this towards more stable uh, condition. Or you can also introduce the larger substitutional atom in the upper part, but away from where the dislocation occurred. So this will create compressive. This is compressive. Will repel the compressive part of this part and then make it to be more stable also. Yeah. This is, I think, this is the similar graph as what we have presented in the earlier slide. In the upper part of the edge dislocation, you have compressive state, while in the lower half, you have the tension state. So impurities tend to segregate at energetically favorable areas around the dislocation core and partially decrease the overall stress field generated around the dislocation core. However, when stress is applied, more load is needed to move dislocation with impurity atoms segregated to its core. Yeah, like this, you have this will create will increase then the yield strength. Small impurities tend to concentrate at the dislocation part, and this will reduce the mobility of dislocation, which then, as a result, it will increase the strength. Here, For example, we have this plane impurity. We introduce smaller impurities. Okay. So this will reduce initially when there is no impurities here. The dislocation can move easily through breaking and reforming the bonding of this atomic plane, and then it will create slip. But when we put impurities here, it will block the mobility of the dislocation, prevent the mobility. The strength will be increased. Large impurities, on the other hand, will concentrate at dislocation on the low density side. Yeah, the low density side means because when there is no impurities here, there is a tensile strength. When you put larger impurities here, it will create compressive field around it. The compressive field will compensate the tensile field of the low density side of the impurity of the of the dislocation. Okay. This is one example of making a solid solution of strengthening in copper by introducing nickel impurity. With increased weight percentage of nickel inside copper, we increase the tensile strength, right? Similarly, the yield strength is also increased. So it will be more difficult for this alloy to be deformed compared to pure copper. So from here, the empirical relation of the yield strength as a function of concentration is the yield strength is proportional to the square root of the concentration. The alloying process increases the yield strength and the tensile strength. So it is harder for this alloy to break. Okay, another strategy for strengthening is what we call as precipitation of strengthening. So this is I think the third method, yeah, which is strain hardening. Yeah, strain hardening through precipitation strengthening. What is precipitation strengthening? Precipitate. Hard precipitates are difficult to shear. Yeah, this is actually similar to introducing impurity, but you are not introducing alloy. You are not making alloy with another metal, but instead you introducing other type of impurity. For example, here ceramics in impurity. The ceramics impurity inside metal. By introducing silicon carbide in iron or aluminum, yeah, large shear stress is needed to move this dislocation towards the precipitate and to shear it. So here we have this precipitation. Dislocation can advance, but precipitate act as the pinning side with spacing ice and slip part of the slip. So very difficult, it will slip. It cannot slip easily. The yield strength is proportional to 1 over S. S is the distance between the two precipitates. If the distance is smaller, which means that you introduce more precipitate, the yield strength will increase because it cannot deform at all. When the distance between the precipitates are larger, you put more distance, the yield strength will decrease. This precipitation strengthening has been applied, for example, to increase the strength of the wing structure of Boeing 767. Here, the black spots are the precipitate formed by alloy inside the aluminum structure. Okay, the last strategy is cold work, indicated by percent cold work. In cold work, you are applying stress to the material at room temperature to deform it, to make deformation of the material at that room temperature. Why? What will happen? That you make the dislocation to be denser, which will create an entanglement between the dislocation. which will eventually prevent that dislocation to move to the edge. So this is done by common forming operation change that will change the cross-sectional area. This is why percent cold work is usually expressed as the difference or the change of the cross-sectional area compared to the original cross-sectional area. To change the cross-sectional area can be done with many ways. One is by forging. Yeah, when you put the blank, which is a metal, inside the die, then you put force, you hammer it, such that then this blank will be smaller. Yeah, the AD, the cross-sectional area, becomes smaller to the original cross-sectional area. Another way is by drawing. You pull that metal between two die. So the resulted cross-sectional area AD will be smaller than the original cross-sectional area A0 by tensile force. So this process is commonly done in steel industries to create stronger product. Yeah. Actually, our traditional empu blacksmith, yeah, that makes keris or sword, use this kind of cold work also to make their keris or sword stronger, yeah, by hammering. Remember, if you see a picture of keris empu, they hammer the keris. Yeah, it is basically a form of cold work. Third way is by rolling, where we put the material inside to things that is rolling to make it smaller cross section. And finally, by extrusion, by pushing the material inside the billet, yeah, using by force, and the extrusion will come in between the die holder. So in under observation in microscope, this is what happened in titanium alloy after cold work. So what you see here as black lines are basically the dislocation inside this material. The dislocation upon after the cold working, they will be denser. Yeah, dislocation will entangle with one another during cold work like this. Entanglement. Remember the movie Tangled? Something like that. The tangled when the princess has hair and the hair is tangled, then it will become stronger. The dislocation motion becomes more difficult when these dislocations are entangled to each other. They cannot move easily again to the edge of the material to make deformation. So this result of cold works is expressed as dislocation density, yeah, as a figure of merit, which is calculated from the total dislocation length per unit volume. In carefully grown single crystal, dislocation density is about 1,000 per square millimeter. When it is deformed using cold work, yeah, the dislocation density increases to 1 billion to 10 billion per square millimeter. If you want to make it weak again, you can do heat treatment. Yeah, you apply temperature, high temperature, so that then it will reorder again. The dislocation will be reordering again to each other. And then the entanglement also, some of the entanglement will be released. As a result, the dislocation density will be reduced to 100,000 to 1 million per square millimeter. So the yield stress increase when the density of the dislocation increases. So upon large hardening, yield strength will increase. When you do only small hardening, the yield strength will not increase that much. Dislocation density goes up. So when in carefully prepared sample is 1,000 and heavily deformed sample could go up to 10 billion per millimeter per cubic millimeter. How to measure the dislocation density? So within a single volume like this, how many we have? This, for example, we have these 3 dislocation. The density of the dislocation will be equals to the length of the first dislocation plus the length of second dislocation plus the third dislocation length divided by the total volume. So here, for example, an example, and dislocation pits refilled by etching like this. So like a gap, a small valley. Yield stress increases when the density of the dislocation increases. Okay. An increase by cold working, we can increase the sigma Y, that is yield strength, due to the plastic deformation. But actually, the number of dislocations are increasing. Yeah, this seems to be paradox. The number of dislocation increases, but it becomes stronger. How come? Because the dislocations, they are entangled to each other. The curve fit to the stress strain response. This is through stress, sigma T equals to C times epsilon T power N. So, stress field of dislocation. The strain fields around dislocation interact with each other, hence they exert force on each other. In edge dislocation, when they are in the same plane, they repel each other, or other if they have the same sign. They can attract and annihilate if they have opposite side. Okay, this one similar like the before slide. So here, when they are opposite to each other, they will annihilate and become perfect crystal. This is actually what occurs also during cold work. When you cold work, you force them to have this dislocation, which have different orientation, different of Berger factor, yeah, like the bottom part here, to move towards each other, and then they can annihilate and form a perfect crystal. So the impact of cold work is yield strength. The larger the percentage of cold work, the yield strength will increase. So this is illustrate the change of the curve. Yeah, at the 0% of cold work like this, you have, this is the elastic region. This is the yield strength. This is the ultimate tensile strength. When cold work is done, the higher the percentage of cold work, the yield strength is increases. Tensile strength also increases. Until here, there is the failure, the breaking stress, the failure stress. Tensile stress increases. However, ductility, the percent elongation, decrease. Okay. So the material which, when you do cold work, they become harder, more difficult to break, but then it will be more difficult to form also, to form as well, because the ductility decrease. As cold work increase here, as we see, when during the 0% cold work, you have like this, yield strength is in this region, ultimate tensile strength is this region, 400 something megapascal. But when you do 4% cold work, it increases a little bit, yield strength increase this region, tensile strength also increases a little bit. When you do much more cold work, yield strength is in this region, tensile strength in this region, much higher, much larger than 0% cold work. Yield strength increase, tensile strength increase as well. However, the ductility here, the ability to form, yeah, the material decreases. Okay, let's have a break for a while, so we'll continue discussion about cold work.